Hello and welcome everybody to SkyTour Radio here on this 27th, one day before the end of February in 2022. It's me, Mark D'Antonio, your host. I want to welcome our Facebook watchers who are watching us on Facebook and our SkyTour live stream audience who's watching on SkyTour live stream. Hi, Tara. How are you?
Hi. Hello. Hello, everyone.
And how are you down there, Daryl?
I'm nominal, thank you. Warp engines are online.
All engines are online. Shields are at 100%.
Yeah.
Okay, at warp factor 1, cruising to the nearest star.
Feels like I'm standing still.
That's right. In fact, it would actually in a real warp drive. You know, in the real warp drive, you would actually be standing still, and you'd be pulling the universe past you as fast as you could muster with the energy that you have. That's the concept of the Alcubierre drive that we've talked about before. And stellar travel, of course, is something that we all long to see, you know, coming down the path for us. And there are labs currently investigating stellar travel. But for now, I think it's important that we learn a little bit more about the cosmos and give us a destination to go to. And there's one particular instrument that's out there right now that might help us figure that out. And I know that you probably know that, Tara, and I'm sure you do too, Daryl. Obviously, we're talking about the James Webb Space Telescope. And the James Webb Space Telescope is just an incredible instrument. Now, compared to our SkyTour live stream telescopes and our remote observatories, it's hands down tens of thousands of times better. And we do a fantastic job, okay? Just ask Daryl, he'll tell you, right, Daryl? Okay, and Tara will too, right? You know, but the point, the point being that the James Webb Space Telescope is about 1 million miles away from us, and the latest updates are extremely promising and show profound progress. So, for example, you know. We talked about the James Webb Space Telescope going out to what we call a parking spot in space. Well, there's 5 such parking spots. Okay, if we look here at this diagram, you can see L1 just to the right of the sun, and to the right of that you see L2, which is where the James Webb is. Then you see L3 on the other side of the sun, and then you see L4 and L5. L4 and L5 are spots that are right in our Earth's orbit. Okay, they're several degrees ahead and several degrees behind our Earth. That said,
60 degrees.
Exactly.
Oh, isn't L3 as well?
L3 is actually on the other side of the sun, and if you consider it, L1 and L2 and L3 are in the plane of our orbit. L3, you can say that it's in Earth orbit, yes, but L4 and L5 are special compared to L1, 2, and 3.
Oh, okay.
The reason is L1, 2, and 3 are what are called metastable Lagrange points. That is to say that if you were to put something there, you have to give it energy to keep it there. And, you know, it's not an insignificant amount, but it's a much smaller amount than you would have to input into the system to keep it there anywhere else you put it. Okay. But then for the other Lagrange points, L4 and L5, okay, those are what are called stable Lagrange points. L1, 2, and 3 are metastable. L4 and L5 more easily balance the gravitational forces on them while they're also orbiting the sun.
L4 and L5 are also called Trojan points.
Right, and there's a reason for that too. And one of the things that, as Daryl just mentioned, Trojan points are also places that can collect more than satellites. They can collect asteroids. And the Earth, actually, we just found that the Earth has a Trojan asteroid or two in its orbit. But don't worry, they're never going to come to us. Okay, they're in a stable position, as we said.
Famous last words.
If we ever become a truly spacefaring race, L4 and L5 is going to be where the action is. Like,
I agree.
Space colonies in the future, I bet they'll park them out at L4 and L5.
And if we ever have the technology to harvest an asteroid, we might figure out a way to send it into an orbit that's L4 or L5 to make it easy to get to and come back from. So we can harvest it. Now, that makes it a lot easier than going all the way out to the asteroid belt, right? Although it might be fun to be a belter. I actually wrote a sci-fi story once called, I forget the name, but it was about asteroid miners, and I called them belters. And it turns out that that term has also been used in some sci-fi, which is, it stands to reason,
Oh, yeah.
And so it makes sense that you'd go to the asteroids to find valuable minerals and so forth. I think that it's a very, very likely place to do that. So the point about L1, 2, 3, 4, and 5 is the L2 on the right there. You see that orange ellipse. That orange ellipse is actually the elliptical orbit of the James Webb. None of this is to scale. Okay, the Earth is really not that close to the sun. Okay, and it's really not that big compared to the sun. And L2 is not that close to the Earth, and the orange ellipse, is not nearly the size you see it there relatively. What is important is that in order to keep the spacecraft, James Webb, stable enough to stay at L2, because it's a metastable, not entirely stable is how that reads, a location, it has to actually orbit the actual L2 point. It's just kind of weird, right? Because that's just an empty point in space. But with fancy physics, there's a way, using the fact that the satellite is also orbiting around the sun, there's a way to make it so that the satellite will carry on a roughly elliptical orbit. It's really an odd-shaped orbit when you look at the actual shape of the orbit, okay? But effectively, it's this elliptical orbit around L2. All right, that said, now the satellite's there. James Webb is in place. Everything works. Everything just, connected the way it was supposed to, unfurled the way it was supposed to, and functioned the way it was supposed to. And so a few weeks ago, they actually took an image using the entire set of mirrors on the telescope, and they got this. And you look at that and you go, oh, what's that? I look stupid. Okay, I get it. But each of those images, if you count them, there's 18 of them. And that corresponds to the 18 hexagonal mirror segments on the James Webb Telescope. What that says is each one of the mirrors put light through the central axis and into the instrument package on the back of the telescope. So that means that the light got there. Now, that led to a new thing that occurred because these mirrors were not aligned, right? They were all just aiming light into the secondary mirror, which you see at the top of the image there. The stalk is folded in this particular case. And then down through the center where you see that black squarish tapered box there, that's actually the entry point for the light. So the light hits the big mirror, goes up to the small mirrors when they're sticking out, and then they go down through the center of the mirror to the instruments. Well, each mirror did that. Well, now each of those mirrors moves on its own, and you have to move these mirrors around just so that all those 18 images get coalesced into just one. And this is the result they just released.
Oh, that's so cool.
It's perfect. It's perfect. Daryl and I and Tara were talking earlier. This you can see the airy disk around this star image, showing that the collimation, that is the alignment of the mirrors, is literally probably as good as it can get. That's not bad at all. So a little bit more work, and the James Webb Space Telescope will be ready for the prime time.
I'm kind of curious about the shape of the diffraction spikes in that image. I mean, I think I can get 6 because there's 3 secondary supports for the secondary mirror.
Yeah.
And 3 supports would make 6 spikes. But then you also got 2 spikes at 180 degrees on the left and the right.
Yeah. If you think about it, that looks to me like it goes to the center of each hexagonal segment, doesn't it? The leg of each hexagonal segment. It looks like if you go to the center, if you draw a line from point to point, you get a hexagon. Right?
Yeah.
So it looks like there's probably, because we know that if we actually just look at this again, okay, if you notice at the bottom of this image, you can see one of those hexagons, those little tiny hexagons. There's 18 of them in this image. And that bottom one, it's flat. So it's a flat segment. So it's going to bisect the segment. This reflection is going to bisect the segment. So I have a feeling that it's probably due to something like that going on in the system. With the fact that it's a hexagonal mirror. And to the telescope, each of those mirrors has a defined edge to it, right? And it's a hexagon. So there's a sharp edge that makes it like a 6-sided, sharp-edged shape, So that's kind of what we're looking at there. Maybe that's what's responsible for this. I don't know. I'm not an optical physicist, so I can't tell you. I'm just guessing. But it's 6-sided. And the mirrors are 6-sided. So there's got to be some relationship.
Yeah.
But that's just my thought. I don't know. And now back to us. Hi, we're back.
Hey, I have a question.
Yes.
Are those images considered that telescope's first light? Is that what they call it?
You're right. Actually, this would be considered first light. This is effectively would be first collimated light, at least that's been released. Certainly the team has seen hundreds and hundreds of images that we have not seen. So this image, when released, was probably not the first time it was released. First time it was seen. It was probably seen in a variety of iterations for a number of days.
And I'm sorry, did you say what that is the image of?
It's actually the image of a particular star. I don't remember the star name. They actually gave the star name. But it is an image of a particular star. Which I think is pretty cool.
Yeah.
First light, conventionally speaking, Tara, is when they point the telescope at an object for the first time. I guess you could say that's first light. If Mark says, they identified the star. But yeah, it's like when I built my first telescope. Well, my first light was actually, I guess my first light was Polaris because I polar aligned the telescope. And then the first thing I looked at after that was Comet Hyakutake back in 1996.
That's right.
I always called that my first light official.
That's cool.
Go ahead, Daryl.
Well, one thing I mentioned this last night, they still have so much to do to bring the telescope online that don't be in a hurry to see any images probably for 2 to 3 months yet. And there are some sites on YouTube that are purporting to be showing images from the Webb telescope, and they're fake. So don't believe what you see. I mean, the timeline, I think, is like June. They still have to bring all the instrumentation online and get it dialed in. There's a lot for them to do before we actually see the telescope go to work.
Right. There was enough to do to get this image out there and get this alignment done. And as I said before, when we first started, we do have our SkyTour live stream family of friends watching us. We got lots and lots of comments showing up in the comment section. Thank you guys for being here. I see a whole bunch of people. I want to publicly thank Isabella Melamed from Sofia, Bulgaria. She's here. And Isabella, in our SkyTour live stream, she will actually take our live streams and go through each object that we talk about, each conversation we have, and she will categorize them and turn them for every video into a table of contents. I mean, what can I say? That is just above and beyond. She's wonderful.
Awesome.
Isabella rocks.
Wonderful.
She does.
As Daryl says, Isabella rocks. It's absolutely right. So I want to thank you, Isabella, for doing that. And Consider this your public thank you. And there's a whole bunch of other people that are here that I recognize from our streams. I want to thank you guys for being here. We have people from all over the place. Vera's from Brazil. We got other people from Australia. We've got people watching and listening all over the place. And so this is the first time we've actually streamed to SkyTour live stream with our weekly radio show. And as you can see, it's not entirely just radio, is it? Okay. And that's cool. So I want to thank you guys for being here. We're also on Facebook too. So anyone watching on Facebook will be able to comment and check us out. And we are looking at the comments. We're watching everything you say. So it's fine. But it's nice to see you guys. Now, tonight, we wanted to talk about, that whole process with James Webb. And we went through and talked about the different instrumentation that the James Webb has, and that's cool. It's actually infrared. And I just want to remind you all of why the James Webb Telescope is looking in the infrared, and for that reason, my lights are red. Okay, I'm in a nod to the James Webb Space Telescope spectrum. I'm using my red lights tonight. So basically, when we look at any star from in space or a galaxy or anything that anything that emits light, okay, we see a spectrum. We see red, orange, yellow, green, blue, indigo, and violet. The whole rainbow, right? Well, that rainbow, all right, can shift depending on how fast the object is moving. If it's moving away from us at high speed, it shifts into the longer wavelengths, into the red. How do you know this is true? Because it happens with sound as well. When a train's approaching, it's going, and you hear the sound go down. Okay. Well, that change in pitch is not noticed if you're riding on the train. On the train, the whistle's going beep, but as you're looking from the ground, it goes beep. Okay. That's because as it's approaching, those waves are compressed and they actually turn higher frequency. In the light world, that means blue. So anything approaching us is shifted toward the blue end of the spectrum, higher frequency. Shifted toward the low end of the spectrum when it's going away from us and they're getting dragged out behind it. So if a galaxy is heading far away from us, it's moving very, very fast from us as we see in the universe, then its data, all of its light gets shifted into the red. And unfortunately, there are galaxies and whole chunks of the universe we've never been able to see because they're so far away and moving so fast away from us that all of their information, all of the data coming to us from them is shifted fully out into the infrared part of the spectrum.
Yeah.
Far beyond what the Hubble could even see. And it had an infrared telescope. The James Webb sees out to 24,500 micrometers. That doesn't mean much to you, but understand that Hubble could only see out to about 5 or 6.
Yeah, and that's called cosmic redshift.
Right.
Yeah, and I have a question really quick, Mark. If you were really an infrared, wouldn't you look like the Predator?
Yeah, but keep in mind, there is one sliver in the James Webb Space Telescope spectrum, the one I'm using here, which is actually in the visible part of the red spectrum. It's really right at the very end. But you're absolutely right. I would actually be invisible if I was in the full infrared. You know, I would shimmer if I was affecting the air around me. Okay, cool. That's all you'd see. You know. So, of course, that brings to mind, we think about this, we have to retrain our technological eyes to be able to see things in the universe. But what about, and this is a side note, but a cool one, what about creatures that may have developed on a planet where their star was putting out a lot of high frequency light, blue light? Ordinary eyes couldn't develop there, nor could an ordinary being like us. It had to be some type of really, really robust life form to be able to handle that kind of energy without being destroyed. It has to be protected in some way. On the other hand, what if you're by a star that is so low in its overall light output? We call that luminosity. Its total energy output is its luminosity. So if it's so low in luminosity, what if on the dark side of that world, it was so dark that you developed eyes that were able to actually see beyond the red end of the spectrum and use infrared clues to to be able to navigate. So perhaps your eyes might develop the capability to see in the infrared. I think it's all in how you evolve. Humans have a narrow range.
They'd be a lot bigger eyes, probably.
I imagine that would be true too.
One thing I meant to say with the cosmic redshift thing and the Webb, when we look at the Hubble ultra deep field images, and you see all the pretty galaxies in the picture, well, the faintest, smallest, reddest things we see in that image, as Mark alluded to, those are galaxies that are so far redshifted that that's all we can see of them. And that's one of the main purposes of the Webb, is to bring those galaxies to light, so to speak.
Yeah, actually, that's its primary mission. Its primary mission is stated as being able to see back to the beginning of galactic formation in the universe, something not visible to us, because the galaxies are receding and moving away at so high a speed that their light's shifted all the way into the infrared. So that's why James Webb Space Telescope has infrared eyes.
I would wonder if at some point they will try to do an infrared analog of the ultra deep field.
Oh, I'm certain that they will. I mean, consider this. Daryl knows this, so this is for everybody listening. And Tara, you know this, I think. The James Webb Space Telescope has a 21-foot diameter mirror overall. Yes, it's a hexagon, but its overall diameter is 21 feet, okay? The Hubble Space Telescope was only 8 feet, and the only other infrared telescope that was specifically made for infrared imagery was the Spitzer, and its mirror was only 2.8 feet in diameter. And that showed us things in the universe that were just beyond our understanding. The larger the mirror, the more sharp resolution and the finer objects you can see, right? And the better the resolution is what that is, okay? And so it's something called the Dawes limit. It's something that we're up against all the time in astronomy. And I've used many different types of telescopes in observatories, some not in observatories. And the biggest one I ever used was a 24-inch Cassegrain reflector, the smallest. Well, not the smallest. Smallest was like 2 inches in diameter, and I got it as a 6-year-old. But the smallest professional scope I ever used was a 20-inch telescope. So I've always played in the realm of the bigger diameter telescopes. And I think that's why one day, and I think Daryl understands this very well because he understands the whole concept of the light bucket. He with the biggest light bucket wins, that kind of thing. Oh, yeah. And we call big telescopes light buckets, right, Daryl? I mean, that's yeah. And you had some light buckets of your own. I really that guy down there, okay, you don't see, it's over there. You don't see him much, okay, but I can tell you this, okay, he has manufactured some really interesting telescopes, okay. He sent me a picture of a binocular telescope. I know I keep going into it, Daryl. The binocular telescope he made, just imagine a pair of binoculars like this, right? You hold up to your eye, but just imagine those as big, giant telescopes that are binoculars. And he made one of those. And you have to understand, when you look through an eyepiece, you're only getting the light in one eye. And there are these devices that actually split the light and allow you to see with it's called a stereocular that you put into your telescope, and it shows you two eyepieces, and you look in and you say, wow, cool, I can see with both eyes. But it's splitting the light.
Yeah.
And it's reducing the intensity. It's not giving you more, but less. So what you do is you have two telescopes of the same size, each with their own independent eyepiece, and you look through each of those, it's like, whoa, that's new. Okay, and that's really the coolest thing, the most important thing, and best things in sliced bread, right?
Yeah. Well, one thing, bino viewers, so-called, that you put on a single telescope,
yes,
they help your brain resolve what the two eyes are seeing and sort of blend them so it becomes a smoother image. And you can see more even through one telescope. If you have a bino viewer, I have one. I have a couple. But yeah, the whole thing with two telescopes slaved as a giant binocular is light grasp. What we call, why you have a light bucket. The greater the light grasp, the finer the resolution, and the brighter the images and all that happy stuff.
That's right.
Which is why I did it in the first place.
Yeah, I think that's cool. I had a friend named Jay who lived in Massachusetts, and he had two 5-inch diameter refractors that he put on a aluminum utility ladder that was 12 feet long, and at the other end he hung giant weights, and then he put a pivot point in the middle that these things were bolted to, and you could move them around and like literally look at the sky. You could move them with your finger and they'd be perfectly balanced, and you could look at the sky and say, wow, two 5-inch refractors. And the concept of seeing with one eye is one thing, but seeing it with two eyes changes your whole approach.
Yeah.
Changes your whole perspective. And as Daryl says, more of the brain is in play when you're using both eyes. And so the brain can manufacture more details easier.
Yeah, well, my binocular is not all that big. It's just two 6-inch refractors slaved together. And they're wide field refractors, 6-inch f5, relatively low focal length because wide field is what I was trying to go for in the first place.
That's pretty cool.
But there are other ones out there that are, binocular telescopes were a big deal years and years ago. Guys built 18-inch binoculars, 22-inch binoculars, huge light grasp on those things. But you're talking very expensive proposition when you get into telescopes like that.
Yeah. One of the things I wanted to do, and this is kind of cool. One of the things that I tried to do in my younger years, actually, when I was getting my astronomy degree, was I really wanted to actually create something unique in astronomy. So I thought, and of course, as with many ideas, the more you look, the more you find out someone else had the same exact idea and did it 5 years before you. Okay. But I thought of having a observer's chair where you could just sit down and with a joystick drive around the sky, okay, with the binoculars right here. And I thought of, hey, why stop there? Why not make these like 5-inch binoculars and drive around like a tank turret, look in the sky, have it basically a curved bottom so it could just move on rollers and everything.
Yep.
And I thought, what a great idea. Well, it turns out they're already out there.
Yeah, it's been done.
Sounds cool.
Right.
Sky and Telescope magazine has usually a monthly feature of telescopes people built, and I have seen them on there before. A guy built a big old, like two great big wheels, one on either side of him with a chair in the middle,
right,
and a telescope or two telescopes strapped into that. And the drive motors were made out of electric drills, and he could actually motor his way around the sky.
I love it.
Yeah.
I love it. See, necessity is the mother of invention. And, if you have a need, you want to fill it, you'll figure out a way within your means. And just like with SkyTour Livestream, our observatory, right? I didn't know how to make this building so that the roof would come off. I went through linear actuators that might pop the top like this. I thought of sliding the roof off, and having actuators that move the roof off. I had people advising me on these things. These linear actuators are like door closers that you have. They have the little plunger inside, and if you let go of the door, it goes and just closes gently. Well, imagine putting a motor on those that can push that piston out and bring that in at will. That's what a linear actuator is. It's a door closer with a motor on it. Well, I thought we could use those to actually pop the roof. I like that idea. But then I thought, boy, oh boy, what if something goes wrong with those? I want something reliable. And I don't remember if it was you, Tara, or if it was Marianne, who is also the other person with SkyTour Livestream who's been offering great suggestions. But somebody thought, well, how do garage doors work? I was like, that's it. Why did I not see that? So we actually have a simple garage door opener that moves the roof on and off. And it's mounted in such a way that the roof is pulled off horizontally and comes back on. No springs needed because we're not going uphill and around a corner like most garage doors. We're just going off and on. And it works beautifully. And it was simple to put in. I had to get into the circuit and wire up the controller a little bit because it wasn't really meant for just like a doorbell button that some people have in their garages where you push a button and the door opens, you push a button and it closes. There was a lot more intelligence built into it than I had encountered before. So I had to dig into the circuit, figure out where in the circuit things were going. And that was just a matter of just patience, right? And then I soldered in the connections. I attached the connections where needed, and boom, it works. And it's still working today. Keep working. If it doesn't work, I'm afraid I'll have to say to Tara, can you go out to the observatory? You're the closest one to the observatory.
Yep, I'd be there.
Yeah. So that's, again, necessity is the mother of invention, right? I wanted to get an observatory up and running. I wanted to have people come from anywhere they wanted to enjoy it. Okay. And those of you watching on YouTube right now, you're watching this as if it's a SkyTour live stream. And I appreciate seeing you guys. But now you see the other part of what I do with SkyTour live stream. We actually have the SkyTour radio, which is what this is, the radio show. So I'm glad you could join us. Our family and our viewers, all the people, you guys are amazing. And I think that what is really, really cool here is that everybody supports what we do. You guys are amazing. Our audience is the best audience on the planet. It's nice to not have to talk to everyone as if it's the first time. They know who we are. They know Daryl. They know you, Tara. They know me. Okay. And I have a feeling that those that are just joining probably will stick around for a while because,
I hope so.
Yeah, you have a great smile.
Thank you.
Daryl's
Can I
not
ask
smiling.
a favor?
Yes.
Can I put up a picture or two of my binocular?
I really would hope you would. Yeah.
Okay. Let me try this.
I'd love to see that.
Okay. There's me.
There you go.
There he is.
Now,
Zoom in on that.
There's two 6-inch f5 telescopes, so that's as big as it gets. Sorry.
You sure?
They're commercial tubes that I bought, a matched pair. Where most of the money went actually was the mount. I designed and fabricated that mount myself. I had a little help from some machinists, but that's the telescope, and there's another view of it.
Wow.
Two 6-inch f5 sky watchers. The mount works beautifully. You wouldn't believe how well it works. The motions are very smooth. It goes up and down in altitude and left to right in azimuth. And that's slightly out of focus, but that's the eyepiece assembly. You can adjust the distance between the eyepieces to match, your interocular distance, whatever they call it.
The distance between your eyes.
Yeah, and you can also adjust tip and tilt on the secondary mirrors there to if you have to refine the collimation between the two telescopes.
Wow.
Is that a seatbelt on? Do you have a strap around you?
Nope. It just it's on a really big, tall surveyor's tripod, and you just stand behind it or sit behind it if you're pointing up high enough. That's basically it.
Now see that? Now that's what I'm talking about, folks. Okay, this is the ingenuity, all right, that makes astronomy live. Okay, wanting to dive deeper into the universe and see other things is just an incredible foray.
Did you see what Genghis called him? He called him Double Barrel Daryl.
Double barrel. Hey, there you go. Double Barrel Daryl.
There's your other brother Daryl joke.
That's funny.
Okay.
Yes, it is. That's funny.
I think it's great. Double Barrel Daryl. Thank you, Tara. That's fine.
That's from Genghis.
And
I have about $3,000 in that telescope.
I bet you do. There's a lot of engineering in there that, that doesn't come cheap, because when you actually try to, put something together like that, to do it right, you can't cut corners. We just encountered that out in the desert, Daryl. And luckily Tara didn't have to go fix it. But we actually, in the beginning, I was told we're going to put the power cables and the Wi-Fi system in conduits and run them from the observatory 150 feet back to where we're powering them. And somebody talked me out of it. And it wasn't me, I promise. I thought conduits were the best way to go. But someone talked me out of it. And so I got direct bury cables, the cables that could just be buried in the ground. And when I did that, everything was just fine and dandy until about 2 weeks ago. And 2 weeks ago, power began bringing down the entire solar green system out there from the building. When the building went online, power came down. I was like, uh-oh. Well, they traced it to rats chewing through the cables underground. And it was like, I knew it. Darn it, I should have put those cables in the conduits. I knew it. And that's an example of what happens when you cut corners, folks. I took people's advice who told me, don't worry about the cables. You're not going to have any problem once they're underground. And as the owner of the property told me, the rats got it. And that's where they live, is underground.
Yeah.
It's like,
okay. At least they weren't giant radioactive spiders.
Not at that point. Yeah. Not giant radioactive spiders. That's correct. That was a horrible 50s movie, by the way. Or lava spiders. I remember Lavalantula was this other stupid movie. It's hilariously bad. I watched it because it was so bad. Okay. Anyway, so that's that power system has been fixed. The other thing we did was we added Starlink to the whole system, and we do have Starlink up and running out there. It's handling the other computers other than our live stream observatory, and the reason is because we have to get an additional adapter to connect to our building, and we're going to do that. That's already on the way. I've already ordered it. So I'm just waiting because we're going to go from single-digit upload speeds to tens of megabits per second, 40, in fact, from 2. We're going to go 20 times faster. And in the downward direction, it's going to go, 4 times faster. No, 6 times faster. So we're impressive. We're making impressive gains here, and it really works well. And that's the kind of thing that's really important, and that's the thing that the SkyTour live stream folks here want to hear. People that are here to listen to astronomy, what it means to you is that we're going to actually be more efficient. And one of the things that we pride ourselves on is that as soon as an image is taken, it's shipped right out of the observatory, goes up to the cloud, and ends up on a server that's free for you to go to, look at, and take down all the images you want. Okay. And
awesome.
Yeah, it is awesome. And there's always little issues, little snafus that happen from time to time, but we fix them, and we keep on top of it. Everything needs maintenance, but this hasn't needed as much maintenance as I had imagined it might. We're actually doing pretty good out there, and it's the first. You knocking on wood?
I am.
Yeah, thank you.
Murphy's Law will.
That's right. I'm knocking on particle board here.
Yeah.
But anyway, it's pretty clear that we're having a good time. Daryl always, if I'm not streaming, Daryl joins on the nights that I'm opening up the telescope to do some research work and to check out some things. And the views, to hear him say, with his experience and background, to hear him say things like, "That is just beautiful. Look at how complex that is. That is amazing." It makes it kind of worth it, right? Because you're actually, you're hearing what many people out there are thinking, that you don't often get to hear them, right? All the people in the chat here that are typing like fast and furious, we don't get to hear everything they say. I don't get to read everything they say because it goes by too fast sometimes. But it's good to get that feedback, And Tara, she's been quite a mover and shaker with SkyTour Livestream. For those of you in SkyTour Livestream, she's the reason that there's a door on the building, and she's the reason there's a building at all. She was the foreman. Okay. She's the foreman. She was the foreman who actually oversaw the complete construction of that building. She was there every day, relaying orders and actually making sure that it got done right. And guess what? It did. So
and 115, I think, degrees.
It was 115 degrees. I know that because the one time I went out there to bury some lines and fill in trenches, I ended up in the hospital that evening for 4 hours.
Right. Oh my gosh.
Yeah. So, listen, this is what's going on. And Daryl, of course, is a mainstay co-host on SkyTour Livestream as well. Oh, you're good, man. Just deal with it, brother.
Hydrate or die when you're out in the
yeah.
I'm always hydrating.
I'm never non-hydrated now, no matter what. So, and speaking of you, Daryl, I think what I'd like to do is take us down another path now that actually gives us a overview of, say, what's going on now at sunset, what's to come, and then you have a concept you want to talk about that might involve another planet in our solar system, which I'm prepared to jump into with you when you're ready.
I want to say thanks to Raymond first, real quick.
Oh, Raymond, thank you.
Well, you want me to start the deep dive now, I guess.
Sure, do the deep dive. We call this deep dive with Daryl. And on the heels of deep dive, we've got this one. Tara, okay, has a bunch of questions that she'd like to ask us. And I can't wait to hear that either. So let's enjoy.
Okay, here we go. Am I showing on screen?
You are.
Very good. Okay, as usual, I'm going to start over in the western sky. And the sun is not down yet because I wanted you to see something. There's the sun, and there is the planet Jupiter. Now, you may recall from past deep dives, Jupiter was up here to the upper left of the sun. And a few months ago, it was Jupiter, Saturn, and Venus made a very pretty line, and sometimes the moon would jump up and join them. Well, Venus went away. Mercury came up for a while near Saturn, and then he went away again. And then Saturn dropped off into the sunset. And now we are seeing Jupiter also has pretty much vanished into the sunset. So if I go forward an hour or two, okay, there the sun went away and Jupiter went away. And Uranus is about all there is up there right now. That orange line is the plane of the ecliptic, which we talk about. That's the highway in the sky, I like to call it. That is the plane that the Earth follows, the sun follows across the sky over the course of a year. And that also defines Earth's orbit. And then as we look to the sun for the reference point, that is the sun's path across the sky and Earth's orbit around the sun. And I'm going to go back again for just a second. But I want to talk about something first. Tara, I think you mentioned this when you joined us on a SkyTour live stream a few weeks ago. It may have been in the context of you asked why we never see Mercury and Venus very far from the sun.
Mm-hmm.
But I think you also mentioned planetary alignments at that time.
Yes.
And what you see there right now, okay, whoops, go the other way. You can sort of see a planetary alignment forming right there. Now, Jupiter is going to pass behind the sun because it's farther from the sun than Earth is. And then Jupiter, this is the morning sky right here, west of the sun. Everything west of the sun is in the morning sky before sunrise. Jupiter is going to be joining the other planets, but at the same time, Mercury is going to be passing behind the sun and popping back up in the evening sky for a while. But Mercury will rotate, revolve around the sun and rejoin the other planets. And I'd run out of fingers and toes here to count really quick. But I believe it is in June we are going to have a planetary alignment in the sky, that all the naked eye planets are going to be west of the sun in the morning sky. And the moon is going to be joining them night by night. The positions will change somewhat by then of the different planets, but you'll see, Saturn will probably be farthest west, or I think maybe Mars is. But you'll see all the lines, all the planets strung in a line in the west, in the east before sunrise, in the western west of the sun. You'll see Mercury, Venus, Jupiter, Saturn, and Mars, and the moon will be joining them day by day, marching past each of the planets. It's going to make a beautiful sight, and that's something to look forward to, and something I will get more into as we get closer to June. But for now, this is our sky after sunset tonight. We are heading into springtime. The spring equinox is only 3 weeks away.
Hey.
That's why, like right now, you see the sun has moved much closer to the west. During winter, the sun was setting way over here in the south-southwest, in the west-southwest. And now the sun is marching day by day, a little farther north each day, as we approach the spring equinox on March the 20th. It's only 3 weeks from now, and that will officially be springtime. We'll no longer be in winter. Daylight and nighttime will be of equal length at the equinox, and then the sun will keep marching north as toward summer, and we will have more light than dark starting in 3 weeks. So there's something to look forward to.
That's great.
It is, and it's been a long winter, but I'm going to march ahead a little bit here and go to the south and give us our constellation lines. Okay, here we are a little before 7 p.m. And another sign of winter sliding away from us is 7 o'clock at night. Orion will already be transiting the meridian, being followed by Sirius, the brightest star in the sky. And again, I'm going to march it forward a few hours. There is almost 8 o'clock, almost 9 o'clock, 10 o'clock, 11 o'clock at night now. Orion is heading towards setting. It's more than halfway down in the west-southwestern sky. Sirius has followed it, and the whole winter circle, Aldebaran in Taurus, Capella in Auriga, Castor and Pollux in Gemini, Procyon in Canis Minor, Sirius in Canis Major, and Rigel in Orion. The whole winter circle is west of the west of the meridian by 11 o'clock at night now. Those are sure signs that winter is going away. But hey, look over in the eastern half of the sky, 11 o'clock at night. Here are the stars of spring. There is Leo. There is Bodes and the bright star Arcturus. There is Spica in the constellation Virgo. Something we have forward to look to here. This is, let me see. Come on, show me. Anyway, Coma Berenices, Leo, and Virgo. If you get right in the middle of those three constellations, right in here, it's called the Realm of Galaxies. Yes. And this is why springtime is galaxy season. The Virgo cluster, I'm sorry?
We're going to be busy, Daryl, I can tell you that.
Oh, yeah. The Virgo cluster is right here. Our Milky Way and all the galaxies in our local group, Andromeda, M31, and M33, and Triangulum, we are all headed in this direction because of gravitational attraction to the Virgo cluster. There are more galaxies under the tail of Leo and more galaxies under the belly of Leo and galaxies up in Coma Berenices. If you can see from Ursa Major up here on the top, the Big Bear, starting up here around and above the Big Bear and kind of dropping across Canis Venatici there, the hunting dogs, and down across Coma, Virgo, and Leo. That band of the 1,000 brightest galaxies in the sky, 3/4 of them are right there in that part of the sky. And that's what we're going to be getting busy with. And looking forward to that. Now, Bart, did you want to go ahead and talk about what we talked about first, or do you want to go ahead and do a deep dive on pictures?
No, actually, do what you're doing because that leads to the next part of the discussion. So that's good.
Very good. Okay, I'm going to back up the time and go back to the west. Something I want you to see right now, folks. I'm going to get west at the bottom, and we're going to go back to earlier in the evening. I want you to note the ecliptic plane there again, that orange or red line, how steep that is to the western horizon. Well, this is the time of year to go out and see the Zodiacal Light. It is a subtle, very beautiful thing, and you need to have a good dark sky to see it. You just go out at the last light of dusk after sunset and watch the sky closely, and you will see a rather narrow, tilted pyramid of light climbing up into the sky. And that is the Zodiacal Light. I've seen it a few times in my life. The best was 1997 when Comet Hale-Bopp was near the peak of its apparition over in the west after sunset. I was up near the top of a mountain pass here in Colorado high elevation, very dark skies, and Hale-Bopp was right about here in this part of the sky, and it was huge. Hale-Bopp was, if you stick your hand out at arm's length, Hale-Bopp was bigger than my hand and wider than my hand up in the west-northwestern sky. You can see its gas tail was a little blue spike running on the underside of the comet, and then above it was a large, broad, fan-shaped dust tail. It was very big. It was very bright. It was beautiful. I took pictures of it, but they're on film. They're not digital. I should get those digitized one day. But what really took me by surprise that night, I should have been expecting it, but I wasn't, was the Zodiacal Light was absolutely huge up here in the western sky. This was in late March, and it was just glorious to see. The really neat thing with the Zodiacal Light, it was the very same color as the dust tail of Comet Hale-Bopp.
Yeah, right.
And what I mean by that was both were the color of sunlight. The dust tail of the comet was shining by reflected sunlight, and the dust in the Zodiacal Light was also shining by reflection of sunlight.
Now, Daryl, can I ask a question here? I actually offered something up here.
Yes, sir.
When I first set up the observatory in the desert, of course, I'm very, very careful about light pollution, and did not want to see any light pollution at all out there. Okay, that was a no-no. So you can imagine my concern when I saw this giant spike of light coming from the horizon. I saw it first in the night vision scope, and when I pulled the night vision scope away, because I had just been scanning the ground and looking around the grounds, I saw this pyramid in the sky of light, and I was like, "What is that? Who's doing it? Oh no!"
And then I realized you were seeing LA at first, weren't you?
I thought I was seeing a city or somebody driving down the road, because we're miles and miles and miles on dirt roads out into the desert. So I thought maybe someone was driving long distance on the dirt road, and I had to wait for a while before I started looking at some astronomical things. But it didn't go away, and it didn't change brightness. And I actually got a picture of it with our all-sky camera. And our all-sky camera is a camera that sees 180 degrees around the whole sky and takes images. And this is the image I caught. All right. If you look on the left side, you see that spike of light. It goes all the way from the middle of the left side all the way to the near the top. Look at that. That's the Zodiacal Light. And I didn't know it at the time. And I was looking, by the way, this was in April. It's the other time you can see it. All right. And so I was looking at this and going, holy Christ, this is now we've ruined. Oh no, it's this. Why did I pick this location? It's ruined. Then I realized, wait a minute.
Yep.
I'm seeing the Zodiacal Light. It's supposed to be there. What we're looking at here, folks, what we're actually seeing is light pollution from our own solar system. It's sky glow created by our own solar system. And that's something that when I saw it and realized what it was, I realized that not only were we in the right spot with this observatory, it was probably one of the best spots you could have.
Yeah.
Because that's hard to see that with your eye if you're in anything but a really dark area.
This is true. As I said, it's subtle. But if you get in a good dark sky with a good dark western horizon, you will see it this time of year from February through April. And you will never forget it once you see it, folks. It's subtle, but it's absolutely beautiful.
Yeah, he's right. He's right.
Okay.
And the question, Daryl, comes from some of the other research about where does the Zodiacal Light come from? And I think that maybe at this point it's a good place to kind of divert down that little pathway that we carved since we started talking about it.
Very good.
Zodiacal Light.
Okay.
Keep this up because we're not done with this yet. Because there's some things we want to show that relate to some of our deep dive stuff later. But I have a feeling we're going to be going to a break here soon. I'm not sure how long we have here.
In about 3 minutes, I think.
Okay, we can do this part here in 3 minutes.
Very good.
Daryl's talking about the Zodiacal Light. That glow is actually something that is Well, we thought that it was leftover, for the most part, leftover dust from the formation of the solar system. And no doubt that's true. This is an example of some of that dust. Okay, this is a tiny little 2-micron, it's called micrometer, piece of little 2.5, 3 micrometer piece of solar system dust. Okay, dust from our solar system retrieved by a probe. All right, and so this type of dust can reflect the sunlight and come down to Earth, and it does. We do see that. But when the Juno probe, JUNO, that Juno probe went to Jupiter, it's flying around the poles of Jupiter now and taking spectacular shots, showing us things that we've just never known about the planet Jupiter, the biggest planet in our solar system. But on its way out to Jupiter, between Earth and the asteroid belt, it actually there was a spot where it was encountering a tremendous amount of particles. And these particles were hitting the solar panels. And they were like, uh-oh, something's wrong here, they said. What is this? What's causing this? And, of course, Juno got through it. The solar panels were not damaged, and so Juno's on its mission. But the research continued to figure out what this was. It turns out what this was actually dust from Mars. And the reason they say it's dust from Mars is because they figured the motions of that dust, coupled with the position of Mars, which is dead center in this dust band, okay, that Juno flew through, indicates that maybe the global dust storms on Mars sometimes release particles out into space that trail behind Mars and over time have drawn out into a gigantic band that includes something that we call the Zodiacal Light. It's pretty amazing, you know.
Yeah, I'm trying to post a link and I can't get it to go.
Okay. Well, you know what? Here's the thing, okay? We know that Mars is the dustiest planet in our solar system, okay? And the dust storms go planet-wide on that planet. And if you think about it, take some talcum powder and sprinkle it in your hand and blow. It goes everywhere. The particles are so fine you almost can't see them, right?
Excuse me. Yep.
Time, isn't it?
It's time. Yep.
All right. All right, well, guys, we'll be back right after these messages. And don't go away, because we got a lot more to go.
Yeah, we'll pick up on this.
You got it.
I flew across country, got my manual, and I was ready to go. It starts with some classroom time and hearing expert advice from MUFON field investigators.
I'm Gwen Farrell. I'm a certified hypnotherapist and an experiencer therapist. For about the past 13 years, I have worked directly with experiencers, contactees, and abductees.
It's credited to Ben Franklin, who said, "Do you love life? Then do not squander time, because time is the stuff life is made from."
Then it was off to the desert to learn more. So we have arrived at the site. We're going to learn a little astronomy and, just how to look out for UFOs.
Watch for jumping cactus.
It's also known as jumping cactus, and it seems to just jump on you. Don't even look at it long. I'm telling you, it has barbs to go in and hooks. Don't want to take anyone with urgent care. So stay away from the white cactus, far, far away. Yes, there's rattlesnakes. Yes, there's tarantulas if you're lucky enough to see one. Sometimes we have to just crawl right through here. They don't hurt you. Yes, there's scorpions. They're horrible.
And the parking lot has thousands of splotches that big from where the cars run them over.
Oh, nice.
And so if you go to the lights, there's like 20, there's 50, 100, you'll count thousands.
But don't let this man scare you. It's just like getting stung by a bee or a wasp. You're not going to die.
Sure, whatever you say. But when it came time for sunset, there's nowhere I'd rather be. It was a perfect night full of stars. And some people brought serious equipment. We even managed to find some scorpions. They weren't so scary after all. Then it was time for a good night's rest so we could be up and at 'em again Sunday morning.
Good morning, everybody. Last night was a blast. I'm so excited to be here and hanging out with my awesome Arizona MUFON friends.
Also, I've got a field kit in the back that you can look at that I use, one of my field kits with a lot of nifty electronic stuff in it.
After some classroom learning, it was back to the desert for our practical test.
The practical is you guys proving that you have learned how to do what you're going to learn from John and Stan, teaching you forensic field work. And these guys are the best, so you guys need to consider yourselves super lucky that you're learning this from the ex-Navajo Rangers, because they are the best at what they do.
Who, what, where, when, why, and how. You want to be thorough in that investigation. When you have that sense, trust that.
And just so you know, that sixth sense, everybody has it to some degree. But it's like a muscle. If you use it, you can develop it.
Hoax is where it's obvious, where somebody has deliberately created an event and executed it. It means like they build a drone of some type, put a whole bunch of lights around the bottom of it, make it look like a flying saucer. And you got to find out where the truth lies.
I'm going to have 5 spots out here in the desert, all picked out and all baited with alien artifacts for you guys to find and bag and tag and collect correctly. And then you're going to prove that you know how to do that and fill out the forms the right way.
So, how did we do?
They did tag and collect all of it. Initially assessing the scene, safety was number one. Really, the focus was teamwork.
And they processed the site correctly. They made assignments.
Everybody has been following the guidelines religiously. They were number one. They did really good.
And to wrap it all up, we got our certificates of completion.
Thank you all for being here and having the right attitude and everything. It really, really helps. Thank you, Stacy.
We had a blast and even managed to get a few plugs for the show.
What's up?
What's up? What's up?
What's up?
Join me and Katie Grabowski and Krista Perno live every Thursday night from 6 to 8 p.m. Eastern right here on KGRA Digital Broadcasting. Tune in and find out what's up.
Well, welcome back. And so now we left off, we were talking about the dust that Juno had encountered. And I think, Daryl, you were making some comments on it as well.
Yes.
But did you want to finish your side, and then I will go forward?
Yeah, I can pick up on that. First, I tried to post a link in our general chat, and the darn chat button is right in the way. I can't post it. That covers all this stuff. But Juno, we launched toward Jupiter, and as it was flying out toward Jupiter, it was approaching the orbit of Mars, and it started encountering a lot of dust. And they could do counts with the Juno spacecraft, how much dust it was running into. It passed the orbit of Mars, and then it was approaching the orbit of the asteroid belt on its way out to Jupiter. They were expecting the dust count to go up when they approached the asteroid belt, but the count dropped instead. And again, I wish I could post the links. They were able to model the dust that the craft passed through, and it turns out now, to make a long story short, that apparently Mars, not the asteroid belt or comets, is the source of most of the dust that we see in the Zodiacal Light. As you said, Mars has these planet-wide dust storms that raises the dust high up in the atmosphere, and somehow it is being conveyed from the Martian atmosphere into space. Now, some of the stuff that I had dug up that I can't post, darn it, talks about this, that I had wondered, well, the dust has to achieve orbital velocity or escape velocity to leave Mars and go out into open space where we could then see it. And it turns out they're still working on that. They haven't figured that out quite yet. I have to guess it's something to do with the solar wind. Encounters the dust in the upper Martian atmosphere.
And don't forget that that dust, just so you understand, I was talking about talcum powder before.
Yes.
And Tara said she's familiar with talcum powder blowing all over the place. You can't even see an individual piece of talcum powder, talcum grain, because it's so small. That's literally a very good analogy, an extremely good analogy as to how fine some of these fines are. Some of the FINES, the fines are in these grains on the Martian surface. So we're seeing talcum powder like grains that get sent aloft. That's why Mars always has a salmon colored sky, because these fine grains are always in the upper atmosphere. And it's possible that due to solar activity, the atmosphere expands and contracts, possibly, and maybe in the upper parts of the atmosphere, maybe somehow these particles are getting sheared out of the atmosphere in some way. And now, as you mentioned, Daryl, they need to reach an orbital velocity. But let's keep in mind that the orbital velocity for Mars is a heck of a lot smaller than the orbital velocity for the Earth.
This is true.
So it's probably an easier prospect. Now, keep in mind also that there was a bombardment era. Mars has some really large craters in some places that show some very large asteroids struck the planet. And when that happens, a huge amount of dust is going to be blown off the planet for good. So Mars looks like it does because of an early bombardment era that actually knocked a lot of atmosphere off, as well as soil and particles of dust. All right. And so that's something that we're seeing as well.
Yeah. Plus, I'd have to guess desiccation on Mars, drying out because of the loss of water and loss of atmosphere on the planet. It's an extremely dry place.
That's right. And we've mentioned before that Mars used to have a very, very heavy atmosphere relative to what it is now. And there was a lot of water in the atmosphere. At one point, Mars had clouds, many of them. And it has clouds now, but they're much smaller, thinner, more wispy carbon dioxide clouds in some cases, in other cases, water clouds. But those clouds were just they're just a vestige of what used to be on Mars. And the water content in the atmosphere is very low. And there used to be a time when the water would be in copious amounts in the atmosphere, but the ultraviolet light hitting those water molecules would drive the H2O apart. H2O, right? Water. Okay. We survive on it. Mars probably did too. But you separate them into hydrogen, which leaves the atmosphere because it's so light, especially on a planet that has a lower gravity. And the oxygen, now that's heavy relative to the hydrogen and will eventually settle down into the ground, where it combines with other materials in the ground to oxidize them. And that's where we get the color of Mars. Mars is red because it rusted, right? Yep. And so we see a lot of Fe2O3, 2 irons and 3 oxygens, Fe2 and O3. And that's rust, all right? Iron, these iron oxides, otherwise known as hematite, various flavors of hematite as well. And when we look at the Martian blueberries that we saw on the surface of Mars, little round balls that seem everywhere on Mars, well, those are formed potentially in the presence of water, and they are also forms of hematite. And Daryl showed me a picture earlier today of a very strange feature on Mars that looked almost like a piece of coral. And that image, I don't have it here, Daryl. That's my mistake. I should have had that brought up too.
I don't have it with me either, offhand.
That's okay. That's okay. Bottom line is, this to me looks like a very strange hematite formation. Now, maybe it formed in veins and this was exposed over time. Who knows? Mars has an incredibly complex history. And we have erosion here because of our atmosphere. What it looks like on the surface now is not what it looked like in the past. How many of you know what Devil's Tower is? Raise your hands. Oh, wait, I can't see you. But Devil's Tower is a gigantic, what looks like a tree stump sticking up in Hewlett, Wyoming, all right? The northeast corner of Wyoming. And what it is it's an exposed magma intrusion, meaning that was underground. It didn't come up. The ground was eroded away from it, exposing it. And that's what happened there. And it when you look at it, you realize the ground was eroded over 800 feet in depth from around this location to expose it. So we have this erosion here, which changes what we see, and what we see, we say, oh well, this is our planet. This is what it looks like. But it eroded to that. It eroded to become that. On Mars, we don't have that. We have some erosion based on wind, but we don't have erosion based on water anymore. So the scars left by water in the distant billions of years past is still there, and we can still see it. We still see where water snaked around a crater that had blasted a hole and then made a giant wall of rubble around it. We see the water, how it went around that crater, making a teardrop shape on the lee side, just like a river on the Earth, okay, where there's an obstruction. So Mars is like a view into the past history of our own planet, you know, and in the same way that it's sort of an alternative history of our planet, okay, when you look at Mars now, we go all the way to Venus now. On the inside, heading closer to the sun, Venus has an atmosphere 90 times as dense as ours. However, it's also an analog to what Earth used to be. And it has to do with the fact that our planet had an atmosphere that used to be as dense as Venus's atmosphere is. Right? And then our atmosphere thinned out as well because, for one reason, it rained. It can't rain on Venus. So the atmosphere never could get rid of a lot of the materials in the atmosphere and drive them down into the soils to create cycles of carbon and water and so forth. That didn't exist there. On the Earth, it did, because we're at that not so hot, not so cold location around the sun we know is the habitable zone, right? The green zone. Yay.
Just right.
That's just right. That's right. Mm-hmm. Right. We have porridge that is just right, Tara.
Yum. Mm-hmm.
That's right. So anyway, so that's that. Now, I know that we've now considered that Mars might be responsible for the Zodiacal Light. So that said, let's turn it back over to Daryl and let him finish, because I'm sure he's wondering where the heck this went. There you go, Daryl. Sorry.
No worries. Okay. Well, we're going to move back over to the south. This is at about 8 o'clock at night, 8:21. And here is Orion. Here's Taurus the bull. There's Aldebaran, his eye. There are his horns. Here is Sirius and Canis Major, the brightest star in the sky. And all this makes the winter circle. And if you draw a line from Rigel to Betelgeuse, you get the heavenly G. We're going to head over this way in general. And I'm hearing a funny noise. Hopefully we're still carrying on. Can you hear me okay, Mark?
Yeah, everything's fine.
Very good. Sounded like somebody's trying to play the piano. That we're going to do the deep dive now, and I bet we're going to head over into this general area where Mark has been taking some really cool pictures. And I'll hand it back to you, Mark.
Oh, okay. Where do you want to go first?
It's up to you. Your pictures.
Okay, let's actually go to Alnitak. So why don't you zoom in on Alnitak? I think Stellarium Online shows some of the imagery that's there, right?
Yeah, very good. Going to Alnitak.
Now, Alnitak is that leftmost star in the belt of Orion.
Right there.
And you have Alnitak, Alnilam, and Mintaka. Interesting thing, okay? Daryl, if you could zoom out a bit to show the whole constellation a little bit, just a little bit more. Sorry. Okay, get Betelgeuse. There you go. Okay. If you look there in the upper left, Betelgeuse in the upper left of Orion there, Betelgeuse is now a red supergiant. But it wasn't always so. As a matter of fact, just a few million years ago, Betelgeuse was a very bright blue, hot, young star. All right. And Betelgeuse is still young. When you think of red supergiants as old stars that are about to go and die, well, not really. Betelgeuse is actually a very young star that's evolving very quickly. And so when we look at it now, if we put it where the sun is, it would go out past the orbit of Mars, right, in its diameter. That's how big the overall size of Betelgeuse is, all right? But Betelgeuse was an O-type star, the hottest and bluest stars that there are in the universe. And it very quickly used up its hydrogen and started to pulsate and use more things that it could fuse into new elements like we see in our periodic table. And those new elements, all right, which are, of course, this periodic table that we've all hated from chemistry class, right? Those new elements end up going into planet building processes and other star building processes. Well, down next to Alnitak, okay, which is another hot blue star, all right, there is a gorgeous, absolutely stunning location of nebulae that just is, I say, to die for, okay? But if you were there, then it would be to die from, okay? Let me just give you an idea of what I'm talking about here, all right? And I'm going to just share the screen to give you an idea of what we're talking about. Okay, this right here is the beautiful region around Alnitak. This is Alnitak right here, right? And if we zoom out a little bit, we can see that Alnitak is illuminating this nebula right here. This is actually called the Flame Nebula for obvious reasons. Doesn't it look like a flame?
It's burning.
Right, it does, right?
It's gorgeous.
And it is hot. There's no doubt about it. It is hot there.
Yeah.
And then this is all dark nebula in here, dark dust. And it's also mixed with hydrogen gas, which you see glowing reddish orange. Actually, it's typically supposed to be red. All right. It looks orange just because of the way I processed it. But this is a mosaic. This is actually 4 different images. It's one image here, one image here, one image here, and one image here. And then I put them all together, right? A beautiful, beautiful mosaic showing these stars. Now, this Horsehead Nebula is dark nebula. Dark nebula is composed of this stuff, okay? These same dark, these dust particles that we see out there. Now, these can have a base of silicon, and then they get coated with ices, okay? Here's an example of a particle, okay? A silicate core in the middle, and around it you have different ices. On the left, you have CH3OH, methanol. You have water ice. And UV light hits it from other stars, and it drives off other materials that make these reaction products, which come off. We get water coming off. We get carbon monoxide. This makes a slurry of planet building materials in these nebulae that we see here. All right. So when we look here at something like this, we are looking at a universe building location. This is an area where you can build new stars and new planets. You know, the Horsehead Nebula is called a dark nebula, right? And, you know, we look up close at it, and you can see that the nebula itself is a really interesting looking filamentary object, kind of like a horse's head. That's, of course, hence the name. These faint lines are Starlink satellites that are going through the view, okay? We find now that we can no longer take any pictures without a satellite or two going through. And then moving down, we see all these many different clouds down here. These are all billowing clouds of dark dust. Look at this right here. This is a beautiful area. Look at that gorgeous tongue of dark nebula sticking out. And it's also got a mixture of hydrogen in it that is being ionized to glow red and like this. And the star doing that is this guy right here. This is Sigma Orionis, a very, very hot star system. It's a star consisting of more than one star. Possibly up to 6, you know, and that's in the region of Alnitak. This is all that was there. Now, we did this all in one night, and the people that attended SkyTour live stream actually got to watch it happen. So they saw each of these 4 frames almost like you see it here. And then we just put them together to show them later because we couldn't do that live. But anyway, so that's the Alnitak region. Now, Daryl, if you wanted to go on to the next region, let's go to M78, Daryl.
Okay. Whoops. Sorry, my mouse is flaky.
Yeah, I know that's the problem with these online apps.
It's not that. There's M78 right there. M78 is just up to the upper left of Alnitak.
Mm-hmm. Right.
There it is.
Yep. Now, what that is interesting to me because Messier 78 is a beautiful little. I say little. It's a reflection nebula. All right, and I did a quick composite today. I didn't try matching colors because I only did it just for the show. All right. So this is that composite. This is Messier 78 right here. Right, and you'll notice the edge of the line of the edge of the photo. Okay, but if you notice again, all this black dust. This black dust is in front of the bright nebula behind it, and it's glowing blue back there because the dust is actually scattering the blue light from the stars. It's a characteristic that makes our sky blue. The same reason, right? It scatters the blue light. So then this particular nebula is also right next to another nebula, this big, giant red nebula. This is actually a very, very famous landmark. This is in Orion now. So Betelgeuse is just down to the lower right here, out of frame. Alnitak. This red object right here is the remains of an ancient supernova. And for all we know, what's left over, maybe that the shock wave from that supernova in the beginning could have spurred all the star formation we see in Orion today. We don't know, but I think it's pretty cool. And I know Daryl likes Barnard's loop. This is actually Barnard's loop right here that we're seeing. All right. And I don't know, Daryl, I'm actually looking forward to taking a photo of the entire Barnard's loop at some point. I'm amazed at how well it comes out. It's so easy to capture out in the desert.
Oh, yeah. Barnard's loop is notoriously difficult to see by eye. It photographs beautifully, though.
Yeah.
I have old piggyback shots of the entire constellation of Orion, and Barnard's loop is unmistakable. Can't avoid it.
No, it's beautiful.
I have a quick question, if I may. Okay, the blue light up in the top right, where there's the dark nebula and the blue light's being scattered. Does that mean it's coming towards us, or is it a totally different thing than what you were talking about earlier?
Very, very good question, Tara. That's an excellent question because I can see how that could be confusing, from blue shift and red shift.
Right.
This has nothing to do with the direction the light's coming from because it'll look blue everywhere, no matter which direction the light's coming from. The light's always going to be coming from there, okay, when you're looking at it. But what's happening is the particles of dust, this stuff that I was telling you about, this stuff right here, okay, this stuff likes to take the blue light from starlight or from our sun, for instance, if it's in our atmosphere as particles of pollution or whatever, volcanic eruption dust, and it likes to take the light, absorb it, and kick it out in all directions. And that process is called scattering, Rayleigh scattering in particular. And that actually shows that the light coming from a star that might otherwise be white can look blue because the blue light is scattered, right? I mean, and the light, okay, I said that wrong. The light coming from, say, a white star will have a blue tinge to it because it's being scattered by this dust, okay, that we see. But the starlight itself is going to look redder, okay? Just like at sunset, we're seeing the sun through more air, which also scatters sunlight's high frequencies. And so we see blue light in our sky all day long. And at sunset, we're looking through much, 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 much more atmosphere to the sun on the horizon. And so the sun looks redder on the horizon. That's why sunsets are red and sunrises are red. Okay. So the scattering causes that, and it also causes reddening. I think, see if I can maybe show you here. If I zoom in here, okay, you see these stars? These stars are in this dark dust. You notice how they're all red?
Yes.
Now, well, some of that could be because of the what's called reddening, all right, caused by this dust. Again, the same reason that volcanic dust causes extremely red sunsets. But it could also be due to the fact that those particular stars might be red intrinsically. They might be red dwarf stars, of which there's more of those than any other kind in the universe. So obviously, we have to be careful in making such pronouncements of these stars. But the blue light is because of scattered starlight. And the red here, this stuff is because of ionized hydrogen, which is mixed in throughout the whole sky. See?
That's cool.
Yeah. All right. Well, now I was thinking, Daryl, maybe go, let's see, how about taking us to the region of the Christmas tree. Put the Christmas tree on the eastern side. And that'll leave us with NGC 2245. I'll explain that, folks. Don't worry. All right. And
okay.
That's right. There you go.
It's right here, isn't it?
Yeah. Okay. So now that region, imagine this. Now, if you look at that region, there is a lot of crazy stuff going on there. Okay. And what that really looks like, all right, is it looks like this. Let me show you. This is that region in the telescope. Okay. And this over here is NGC 2245 and 2247, a couple other reflection nebulae, kind of like that other one we just saw, Messier 78, but this is not it. And then over here is another reflection nebula called that's part of a cluster of stars called the Christmas Tree Cluster. And I think this is the Foxford Nebula here, is it not, Daryl? This right here coming down.
Yeah. There's some debate about that. We can get into that another time. When you zoom in there, the Christmas Tree Cluster is there left of center. The Christmas tree is upside down. That brightest star is the base of the tree, and it's tapering to a point as you go down, and that's a cone nebula directly below the tip of the Christmas tree.
Right. Now, if I actually spin it around upside down to actually flip it for you, then you can see the Christmas tree a little better. So here it is over here. And let's actually zoom in on it. So there's the Christmas tree nebula and cluster right there. Right. And now it kind of looks more like a Christmas tree. This thing at the top, that's the Cone Nebula. That is a very large stalk that's sticking down into this region. These are hot young stars, and they're probably evaporating a lot of the material around the cone here. But something at the tip of the cone is probably more dense and preventing that stuff from being eroded away, at least in our lifetimes and hundreds of lifetimes beyond. Now, going down to this part, you can see more of this beautiful dark nebula. It's just stunning. And you can see this almost in 3D. It almost looks 3D. And I just find that to be fascinating. And so this, again, this is another area of stellar star building and solar system building. And then down here at the bottom, and again, these are all approximately the same distance away, right? Around 1,700 light years or so each. This guy right here is a very interesting little nebula. It's going to be a little bit overexposed, but this is called Hubble's Variable Nebula. Now, you can't see the star that's actually causing this star to illuminate. It's none of the stars you see here. It's actually a star that's buried inside the dark nebula. What dark nebula? The dark nebula that's all throughout here that you can't really see. Okay. It's not an absence of material you're seeing here. It's actually an overabundance of it. It's full of this type of dark nebula. This you only see because other stars are illuminating it and making it look like you can shine. All right. But down here, it's a little bit harder to tell. But the star that's causing this to illuminate is a star that actually has its own disk of dark material that orbits it. And that dark material sometimes casts shadows on this nebula, over the course of days to weeks. And Daryl and I have actually photographed this, and it's looked different every time because it's called Hubble's Variable Nebula. And it's varying in brightness because of that central star that we can't even see.
Yeah, it's a remarkable thing considering how large astronomical objects are, like nebulae. That you look at Hubble's Variable Nebula one day, and you'll see some shadows across the face of it. You can look at it a day or two later, and it's totally changed its appearance.
Yeah, it might be dimmer, it might be brighter, and what we've done is we'll go to Hubble's Variable Nebula with the same telescope, same optics, same position in the sky as best we can, and take a picture of the same duration. And what we get is sometimes very different. And you put the camera settings all the same, so you're capturing it exactly as best you can the same, and it looks very different. There's variability, for those that think the universe doesn't change. Just to give you an idea, everything you see in this image is moving. It's all moving. Okay, this cloud of dark dust has a motion. It's not just sitting there. It's moving through space. And maybe it's being attracted to more dark dust down here. Maybe it's being attracted to something up here in the upper right that we can't see. Maybe it's actually coalescing on itself and was a lot larger than it used to be. Maybe this is isolated in space and is much closer or much further away than the rest of these things in the picture. These are all questions that stand to be answered and can be answered. And that's why we need more astronomers like you. You got to get out there and do this. This is so cool. So this is that wonderful location, the Christmas tree and the cone nebulas. This is something that I think we'll see a lot more of because we're going to be doing this. I don't know if we're going to stream after. We're streaming now, actually, on SkyTour Livestream, but I don't know if we're going to stream after this. I'd have to check everything out there to see. But the bottom line is that's really cool. That location is very nice and amazing. And now, Daryl, if you could take us down to the Orion Nebula. I'm going to bring up the last mosaic that I just put together today. I did that cone one the other night. I did M78 just before coming on the air here, and the Orion Nebula just before that. So this is the Orion Nebula, as Daryl's showing you, and just above it is the Running Man Nebula. Now, you think of them as two separate nebulae, but the fact is they're actually connected. They're actually part of the same complex. And nothing can make that more clear than when you look at this view. This is the Orion Nebula, and here's the Running Man. Well, if we zoom in on this upper right side here, okay, you'll notice there's the Running Man, and you see these beautiful brown clouds filtering down to the Orion Nebula. Yes, it's overexposed. These are satellite trails, okay? But look at all this dust. This dust is being illuminated, but not scattered. It's not scattering the starlight. It's just reflecting the starlight from where the nebula is being illuminated from. And it's just incredible. Actually, you're seeing this for the first time, huh, Daryl?
No, I saw that.
Did I show you this? I just made it today. I don't think I showed it to you, did I?
Oh, okay. Well, I was there when you took the pictures.
Yeah, you were. Yeah. So this down here is an example. Down below the Orion Nebula is another cloud here. And then you've got this really interesting element right here. I'm going to zoom in, but it's, again, we had to use a lower resolution to bring up online here. So you're not seeing it as good as it can be. This is called the 13th Pearl or the Rubber Stamp Nebula. It has a little black T-shaped object, which I've kind of overexposed here to show the rest of the stuff. And what's interesting is there is an overlying dust layer right here. And this is a bright star that's got light that is punching into the dust here and causing the dust to reflect. But then the dust is scattering some of that same star's light down here behind it. So that's down lower into the nebula. And this is higher. This little higher bridge sticking out over it. Isn't this incredible? This is all a fascinating way in which the universe is put together.
Yeah, the blue area above the 13th pearl, bisected by that dark cloud, that and the dark area below the 13th pearl. It is so complex. That's just amazing. That could use
Yeah.
some focal length right there.
Yeah, we're going to take some better pictures of that, you can be sure.
Yeah, that's just tremendous.
Wow.
Love that picture.
I'm thinking, we're actually working on another concept, folks, to take a second telescope and have it work in tandem with what we're using. So we have a magnified view at the same time seeing a wide field view like this. So that's something that I'm actually thinking about as well. I just don't know when to say enough's enough. You just got to keep doing it. Tara, what do you think of all this? What do you think when you look at the sky like this, the universe, the fact that you were part of this, helping to set this up, and now it's delivering imagery like this? These look like paintings.
They're incredible, and they're all so different. And I could stare like just at an inch of that image for probably a couple hours, and just move on to the next. It's really, I find it humbling to some degree, and also just very inspiring, very
Yeah.
inspiring. So
Yeah.
it's just drives me to keep looking for more. It's
Right?
gorgeous. I so appreciate you doing these images for us. It's incredible.
Well, the thing is, okay, what people may forget is that you're an artist. So when you look at a picture like this, you see it not only from the perspective we're looking at it from, but from a perspective that encompasses the beauty and majesty of it. And you can't help but be awestruck by things like this.
Oh, it's incredible.
Yeah, I get
The
it. Yeah.
textures, the colors, what it is, the scales that we're looking at. It's fascinating.
Yeah.
It's
Yeah.
fun.
And speaking of your involvement, I know that looking at things like this, brings you to thoughts, and you ponder and you bring up lots of questions. But I want to just throw one more time to Daryl and say, Daryl, is there anything else you'd like to throw in with the deep dive?
Nope. I think we've covered it. I turned it off, in fact.
All righty, then what I'd like to do is to go into the segment we call Tara's Cosmos, where Tara asks us questions. And I basically told her tonight, any question is fair game. I don't care what it is. So whatever she asks, and we're right here on camera. So, tell everybody else, if we don't know the answer, then it's on us.
Oh man, the pressure's on.
Yeah, right.
You were talking about the electromagnetic spectrum or the visible light spectrum of the James Webb's, how it's doing infrared, because we can't see that. So how do we know that we are aware of all the visible spectrums or all the spectrums that are out there? I mean, maybe we don't have machinery or equipment, technology that shows us more, but are we thinking that we understand the complete range of everything?
Yes.
Well,
how do we know that?
Daryl says that we're thinking that way, but we know that we're not. Okay. There's only so big a spectrum.
Carry on.
Okay. The spectrum is only so large. Okay. We did not have a way to see where the James Webb is looking. And guess what? We have yet to see that. So until the James Webb shows us as far back as we think we can see to the limit of these redshifted galaxies, then we're going to be stuck there. We're not going to be able to see it. But you have to understand, too, that there are certain things that we'll never see because of the nature of the expansion of the universe. The light leaving these objects will actually never get here. Yeah.
It's too weak?
It's just that it'll never get here because of the way the light's expanding and the way the universe and light speed travels. We will never see certain things in the universe ever.
You could say it's on the far side of the microwave background, correct?
That's the far side of the microwave background is the microwave background, if you remember, was the remnant of the birth of the Big Bang in our understanding. And the microwave background, or the CMB as we call it, that actually is as far back as we can see ever, because the universe back 13.8 billion years ago or so, That's when the universe was born. But then around 13.6 billion years ago, it started to get more transparent. It was full of this hot material that was opaque, and photons could not get out. And that's why when they started to get out, we see that mottled background. That's the very, very farthest back we can see with our radio telescopes, because it's certainly not a visual light object. And so that is reminiscent of a time when the universe was finally starting to become a little transparent. And that meant that high energy particles that previously were making the universe opaque were combining to become things that we call atoms. All right, from protons and electrons, they finally combine. Many of them, most of them, combined to form hydrogen, which was a proton and an electron. All right, so that time is as far back as we could ever see. We can never see anything before that. Never. Because there was just no way that information got to us from there. Isn't that crazy?
As far as the spectrum goes, Tara, on the long wavelength end, I guess it's radio, microwave, infrared, or I may have those two backwards.
The other way.
But,
yeah, that's right.
I'm sorry.
No, it's the other way. That's fine.
Okay. On the long end, it's radio, and we can see a lot of that from Earth. That's why we have radio telescopes down here. Microwave, we can detect microwaves. Infrared, it's blocked by Earth's atmosphere mostly, and that's why we're putting telescopes like Spitzer and Webb up there, is to get above the atmosphere so we can see things that we can't see from down here on Earth. Then there's the visible spectrum, which we can see down here. And then you start getting into ultraviolet, which, again, much of it is cut off by Earth's atmosphere. And again, that's where space observatories, space satellites come into play. And from there, you're getting up toward X-rays, ultimately gamma rays. And we have observatories for those too out in space.
Right. But one thing that we never thought we could see until we made detectors to see it, for instance, were gravitational waves.
Yes.
And so with the LIGO and Virgo detectors that we have in the US and Italy, that's the only way we knew. Well, we knew that they were theoretically were possible, but it was actually Einstein, I think, that said we'd never be able to see them or detect them. And he was not correct. We actually could detect them. And we did so with the gravitational waves. So, we understand the spectrum, but what we don't understand is how to have made these detectors to detect them. I'll give you another example. Hawking radiation. Hawking radiation is theoretical, but to detect it is something that's monumentally difficult. So that's something that we theoretically should be there, but we have to be able to confirm it, and we have yet to really see Hawking radiation in detail. So there's a lot of radiative forms that we might suspect, but we don't have the capability of seeing them because our technology just isn't really there. Again, like I said, James Webb is seeing areas in the infrared that we've never seen before. And if it fails, we never will see them unless another James Webb gets made. So you see, there's a lot of progress, but a lot of mysteries out there.
Yeah. As you get into the different regimens of the spectra, you need whole different technologies to look. Like, we're setting up Webb for infrared, and then we get up past visible light into the ultraviolet, and then ultimately into X-rays and gamma rays are the most extreme, I guess. The Chandra X-ray telescope is a totally different critter than the Webb is, for instance, or totally different than the Hubble. It gets into the physics and the behavior of particles at such a high frequency or short wavelength, and gamma rays even more so.
Well, and don't forget, there's one more realm that we can detect them, but it's extremely hard.
Neutrinos.
And you got it, neutrinos. And it's kind of important to detect neutrinos because before a supernova, we would expect, based on our physics, okay, on stellar physics, a burst of neutrinos to come from the star before it goes supernova. So if we see neutrinos, and if we have an adequate way to detect them, every day, like with our little phones, hey, look, my iPhone's detecting neutrinos. Okay, we don't have such a thing. So neutrinos are really hard to detect. But if we could see and do a neutrino study all over the cosmos and say, hey, these stars look like they're going to be going supernova soon. But the neutrino burst comes very soon before the supernova.
Yeah.
In fact, it's already underway when the neutrino burst is released. That's why they're released. So you see, there's parts of the spectrum that we need to be better at looking at. We know that there's material. We know there's particles there, but we just can't get at them.
Yeah. And neutrinos, as an extreme example, where by the time you get to the ultraviolet and X-ray and gamma ray, that we have telescopes out in space to see them, so-called telescopes. To see neutrinos, we do it underground.
In a deep pool of water.
Yep.
Yeah. Because that's the only way to slow them down just enough to be able to see them.
Yeah.
They go right through the Earth like it's not even there.
And they go right through you like you're not even there. There are billions and billions of neutrinos going through you every second.
That's right.
They go right through you.
I've heard recently about a discovery that some neutrinos have mass. And so, Mark, I was going to ask you, could that account for the missing 2% in the universe? Are the neutrino masses that we didn't know about?
I don't know what the mass of the neutrino was supposed to be, so I really can't answer. Yeah, of course it can be small, I guess.
But if there's billions, those are the large and small numbers, right?
No, there'll be a lot of small numbers, so they add up. Yes, I get you.
Yeah.
I'm not so sure, because I'd have to look at the numbers to be able to say. I don't want to be flippant and just say, oh, of course. No.
Well, it's kind of a silly question too, but we're looking for unknown mass, and I just thought, hey, there it is. So
it might be. It could be possible, right? I mean, we just have to. It could account for some of it if there is a mass. Yeah. Okay. Keep in mind that photons of light also act like they have mass as well, in a sense. But light is massless. So what does that mean? Now you're talking about relativistic mass, and that's a concept for a whole nother show. Okay. But if you think about it, gravity, right? People say a black hole has gravity that's so powerful that not even light can escape it, right? And we know that photons don't actually have this mass, right? They have you could say they have mass based on how they act, because they bend in the presence of a gravitational field. And we can calculate what that bend looks like, and from that we can extrapolate something about the nature of the power of the black hole causing it to bend. What's really happening is the black hole's warping space around it. And just like a car riding over a hill, the car follows the contour of the hill. Well, a photon of light is the car, and the bends of space are the hill. So the car just follows the hill. It goes up, it goes down. A photon just follows space. So if space bends, the photon goes around the corner. And that's really what it's a two-stage process. So that's why light can't escape a black hole, because it ends up getting bent so deeply that it just continues to move in a circular path inside the black hole. There you go.
That's so cool.
It is, isn't it? It's crazy.
Mm-hmm. So you were just talking about the curvature of space, and I kind of think of the image where it looks like the Earth is sitting on a net and it falls in, right?
Yeah.
It's kind of a common thing.
It's how we simulated gravity well, an area, the closer you get to the Earth, the steeper the slope, right?
Right.
Deep in that hole, yeah.
But as an artist, what that implies to me is that there's a bottom, and that this Earth is falling in here. So you don't see that net stretching on the top that deeply. You see, so it's kind of hard for me to imagine that.
You know what? You're struggling with a two-dimensional representation of gravity when it's actually three-dimensional.
That's it.
Okay, you've got those cones at every single spot all around the planet. So you've got an infinite number of those cones, which we call the gravity wells, right? So, and they're not even separate from each other. They're all blended together to make one massive warped location. And
Is
so,
it like a moat around the Earth? I mean, is there like a
moat?
space? A space?
No. It's actually just an increase in gravity at every point. If you think of it as measured by numbers, you can measure the gravity from 250,000 feet above the Earth. You can measure the gravity from 110,000 feet above the Earth. You can measure it from 22,000 miles out from the Earth. And you take those numbers, if you add them all up, then the sphere of numbers that's close to the Earth can be really high. And as you get further away, those sphere of numbers drop off. Okay. Now, the point being, how do you represent that to people? Right? So the way to represent it is to just think of it as a giant rubber tarp with a bowling ball in the center that dips down. And then you throw something at it along the way, and it goes around and starts to orbit, and finally it goes right up against it. Right? That does a somewhat of a disservice, because gravity is a three-dimensional construct being represented by a two-dimensional primitive approach, but it does get the point across how paths work with gravitational fields. If you think of it as a plane, but again, it's more like the sphere of numbers. They're big at the middle, near the object, and they get dropped off as you move farther away, and so it's more of a cloud.
This may make perfect sense to you, Tara, or it may confuse you completely. I saw a very powerful presentation many years ago at a convention of the Astronomical League. The guy was talking about the sun and relativity. And if you look at the sun, what we see, it's 850,000 miles in diameter, or 880, something like that. And it was amazing to listen to this guy talk, but the end point of what he said was that if you look at the sun and the mass concentration of the sun, taking relativity into account, that the sun is actually 800 meters less in diameter than it would be if relativity was not in effect. And that 800 meters out of 850,000 miles, that's due to gravity. That's the end of that gravity well you were talking about, that that cone on the grid and stuff like that. That's where it is.
That's cool.
Does that make sense?
It does. You're so smart. That's amazing.
Okay, now repeat it for everybody else.
No, there's a test. Oh gosh.
Nonsense. Well, there you go, Tara. So that's pretty cool. So give us another one.
Okay, well, we have like 2 minutes left. So maybe you can explain the difference between Luna base and Luna right.
Luna base and Luna right?
They're two. Mm-hmm. Do you guys know that? Because one is dark. One of them is dark on the moon, and one of them is the light stuff on the moon. So
Luna base and Luna
right. Yes. Have you guys heard of that?
No.
Okay, well,
she stumped us, man.
I stumped you, Luna base and Luna right. So
Daryl, come up with an answer. This is live, man.
No, sorry.
Well, I think that the difference is the color.
Are you talking about soil?
It is the soil. It's the stuff. So what's the difference? Why is one and why is one the other?
Okay. Okay, that I can answer without, but not with specifics. Only
without
because
Googling it.
Yeah, we're running short on time.
How can I Google? The materials are different colors on the moon. There's no doubt. I mean, there is brown soil, orange soil, white soil, gray soil on the moon. The moon is not just gray, and it depends on the chemical composition at that location, based on what struck the moon, what impactor hit the moon, what material was dredged up from inside the moon, that kind of thing. It also matters how much radiation that soil has been subjected to. That changes the color of things as well. Okay, like Oumuamua was almost like a scarlet red from what they think, because of prolonged exposure to cosmic rays out in the deep interstellar space when it was coming into the Earth, into the solar system.
Can I say real quick, MUFON What's Up is now on Tuesdays at 8 p.m. Eastern Time on KJRA-DB, and we are out of time.
Okay.
Thanks.
Well, there you go. Well, folks, listen, it was great. I'm glad that we had this chance to connect with you. And I'm glad that you guys watching SkyTour live stream got to see it there for the first time, and on Facebook, and of course on KGRADB. We'll be back doing the same thing the next time we broadcast, which should be every week. In any case, you guys have a good night, a good week, and we'll talk to you soon. Good night.
Good night, everybody.
Take care. Bye.